This is another example for calculating velocity profile, but these particular examples will be in the cylindrical coordinate. If you look around, you have searched around, this problem is problems in the textbook written by Professor Wilk. And we have die and wire. This part would be a wire being pulled to the right hand side with constant velocity so that the polymer melt will be pulled along with the wire so that eventually the polymer film would coat on the wire. Okay, and inside the die, this part will be the die. Inside the die, the diameter of the die or the radius of the die is R2, and the radius of the wire itself is R1. The length of the system that we consider is this part, which is L. And at the long distance, the film should have the thickness of delta. Okay, the problem asks for the velocity profile and the flow rate of polymer being caught on the wire. So this is an extension of the system. At first, we need to put the coordinate. Since the system looks like cylindrical coordinate should be proper in this particular examples. As usual, we will assign one axis along the axis of the flow. So in this case, the z-axis for coordinate is supposed to go to the right hand side, and r-axis for cylindrical coordinate supposed to go from the center outward. So either top one or bottom one would always consider as r-axis. Now, if the system is a polymer, now we know for sure that Vc is not zero. In this case, according to the symmetry, V theta is zero. If we can neglect the effects of gravity, so the polymer inside the die is supposed to flow uniformly, and according to symmetry, it does not change with respect to the angle. And lastly, velocity in r direction is supposed to be zero as well, because there will be no flow in this direction. Alright, so next we need to analyze the function of Vc itself. Vc can be function of r, zeta, or z. The first variable would be r. So if Vz is going in this direction, this is Vz, you have to go along the r direction, finding 2 points in the system, asking yourself whether there are 2 points in the system that Vz are not the same. And you should find at least here, at this point, Vz is supposed to be 0 according to no slip condition, because this wall is a fixed wall. It does not move. On the other hand, at this point, velocity of the rod or of the wire is moving with the velocity capital V. So in this case, that means the velocity of the fluid, Vz, is supposed to be a function of r for sure. So it is function of r. Then, if you analyze it further, Vz around 2 theta of the system should be the same according to the symmetry. So Vc should not be function of theta. And if you consider that the flow of the fluid does not have acceleration, Vc here and Vc over there supposed to be the same Otherwise, we cannot maintain the thickness over here and the thickness over there to be constant. So under assumption that the whole die here is filled with polymer, there's no choice but to accept that Vc is not function of z. So now we have Vc as a function of R only. If we want to draw a shell for the particular system, we know that Vc is function of R. The shell size in R direction supposed to be thin, or the dimension in R direction supposed to be delta R. Dimension in theta direction supposed to be full size. That means it's covered from 0 to 2 pi. And dimension in z direction supposed to be full size of L as well. So therefore, our shell supposed to look cylindrical with the thickness of delta R. So the thickness here is delta R, and it should have full length from 0 to L. So the shell looks something like this. Okay, so if I redraw a shell, I should have something like this. This should be our shell, and the width over here is delta R. The length supposed to be L, and it covers to theta of 0 to 2 pi. Okay. Now, since we have velocity in z direction only, so that means right now we have only z momentum. If there's z momentum, there's no flow in r direction, and there's no flow in theta direction. There's supposed to be no momentum in r and in theta direction, but we'll see afterward. So in this case, the flux that we should have supposed to be phi rz, phi theta z, and phi zz. All right. Phi rz is consisted of the molecular transport component tau rz plus rho vrvz. Phi theta z is supposed to be similar, except the component would be in theta and z direction. So rho v theta vz. Lastly, VZZ is supposed to be molecular transport part, tau ZZ, and then whenever we have the same subscript, we need to add pressure in Z direction plus convective transport rho VZ. Okay. So if we try to draw a picture of the flux phi rz supposed to be z momentum transferring in r direction, so it's going in this direction. This should be phi rz going from the center outward in all angles. That would be phi rz. Phi theta z, actually phi theta z is supposed to go around the circumference of the shell, but in this case, because of the fullness of the shell, phi zeta c is supposed to be 0, but I will show you later that mathematically it is 0. Phi zc should go in z direction. The z momentum should be transferred in z direction, going into this area, the annular area here, going in and going out. This should be phi cc. Alright, if you analyze, we know that VR is 0, V zeta is 0, Vz is not 0, so this term must be kept. Okay, for tau we need Newton law. Now, if you look into the del dot V, this term, we can take that for liquid, del dot V supposed to be 0 because it is incompressible. But we can always look into the each component. In this case, VR is 0, V zeta is 0, and Vz is not function of z because Vz is function of r in our case. This term is supposed to be 0. So del dot V is 0 here. That makes this term, and that term will be 0. Alright. We already determined that VR is 0, making tau RR to be 0. V zeta is 0 and VR is 0. Tau zeta is 0 as well. For tau ZZ, Vz is not 0, but it is not function of R. It's not function of Z. This term is 0, so tau ZZ is 0 as well. Next, V zeta is 0, VR is 0, so these two taus, tau R zeta and tau zeta R, are 0. Similarly, Vz is not function of zeta. This term is supposed to be 0, and V zeta is 0. This turns to be 0 as well. Lastly, we know that VR is 0, and then Vz is a function of R. This term must be kept, so this is not 0. So if you go back here, you see that tau Rz is not 0, making phi Rz to be non-zero. But tau zeta z, this term is 0, making phi zeta z to be 0. So in our picture, we can just delete this part. And then tau zz, this term, is 0. So we only have two terms left, pressure and bulk transport. Phi cz is not 0. So now it's time to do the momentum balance. So if we start from looking at this picture of the shell, we have two surfaces. The first surface is supposed to be this surface, the annular surface going in and going out over here. This surface, if I call this one to be top and bottom surface of the shell, we can define in term to be flux relating to phi cz. So flux of phi cz should start with pressure in z direction at z equal to 0 plus bulk transport Vz square in this case, because Vc over here and Vc over there are scalar terms that we can multiply them together to get Vz square at z equal to 0 as well. So this will be the flux, and we have to multiply by the area perpendicular to the flux, and the highlight area of the ring here, the highlight area supposed to be the inner circumference here, which would be 2 pi r multiplied by the thickness. The thickness here supposed to be delta r. So therefore we need to multiply this by delta r. The area would be 2 pi r delta r, as if you cut this highlight area and then spread them like this. So this should be 2 pi r, and the thickness here is delta r. So the highlight area here is supposed to be the same area as this area. This assumption can be done only when delta r is very small, so that the length on the top here and the length on the bottom supposed to be really close, and you can neglect curvature. Then the area, we can just simply say 2 pi r delta r. For the output term, it should be exactly the same, except the location appears at z equal to L. The area should be the same, because the area for input and the area for the output supposed to be the same, exactly the same. So the next area that we need to consider supposed to be the side of the cylinder. On the sideway, which has the length over here, this is sideway. Let me write it down as side. The input term now should be related to phi Rz. This is flux going through the side of the cylinder. So phi Rc, according to what we calculated over here, you get phi Rc to be tau Rc. So the in term supposed to be tau Rz at location of R multiplied by the area perpendicular to the flux. If you go back here, the area perpendicular to the flux supposed to be the side area of the cylinder. The input flux going here, this is input flux going into the inner circumference of the circle of the cylinder. So the inner circumference supposed to have the area of 2 pi r times L. On the other hand, for the output, tau Rc takes place at R plus delta R, because output is going here. It's shifted by the distance of delta R. So the area perpendicular to the flux is supposed to be outer circumference of the circle. So it should be 2 pi r plus delta r times L. Alright? In other words, if you look from the top, here is R, Here's R plus delta R. So the flux going in, this is flux going in, this is flux going out. So the area for the flux going in supposed to be this area, 2 pi r times L, and the outer flux going to the outer circumference, which is this area, that would be 2 pi times r plus delta r times L. Alright, now if you look further, the input and output on the side, this term and this term, can be made to the same form. If I take 2 pi L out, the rest that I have can be R tau RZ, the whole thing taking place at R. For output, if I take 2 pi L out, what I have inside supposed to be R tau RZ at R plus delta R. In other words, if you take R plus delta R over here, replace to this and replace to that, you get the same thing on this line. You get this part. Okay, but now you can convert the input and output into the same format. Once you're done, then you can take them together into the balance, because for this particular problem, the external force is equal to 0, because the problem states that the gravity can be neglected. Then, if you take in and out terms together into the balance, let's start with the top two, 2 pi r delta r times the pressure at Z equal to 0 is atmospheric, and the pressure at Z equal to L is also atmospheric according to the problem statement. For the bulk transport term, the first term, the input term, should be Vc squared at Z equal to 0 subtracted by rho Vc squared at Z equal to L. This is supposed to be input and output term for the top and bottom area. Then we added by the input and output term for the side, which is 2 pi L times R tau RZ, the whole thing taking place at R, subtracted by R tau RZ at R plus delta R. Everything here combined equal to 0 at steady state. We don't need to add force because gravity is negligible in this case. So, if you divide the whole equation by 2 pi, these 2 pi's will be gone. If you divide the whole thing by L and delta R, oh, by the way, this term is already 0. They cancel out. And you should also see that Vc at Z equal to 0 and Vc at Z equal to L, these two terms are the same, because we stated earlier that Vc is not function of Z. So therefore, these two terms cancel out. They become 0. Alright. So if you divide the whole equation by L delta R, we will have divided by delta R equal to 0. And according to definition of differentiation, this term should be minus d of r tau rz by dr equal to 0. After taking limit delta r approaching 0. Alright. If you take integration, you end up with whatever inside the integral to be constant C1. Then, according to Newton's law, we know that tau rz, this term, is minus mu dvz by dr. Please note that I use total differentiation because vz is function of r only. Then there's r over here from this term that would equal to C1. Notice that I remove this minus initially because the right hand side here is 0, but the minus here appears again from Newton's law of viscosity. So if I take r and mu to the right hand side, I can write equation to be minus C1 over mu r, which can be integrated to get Vz equal to minus C1 over mu logarithm of r plus C2. Let me call this equation to be the first equation. In this equation, there are two variables or two unknowns, C1 and C2. So therefore, we need two boundary conditions. The first boundary condition is supposed to be relating or supposed to tell you velocity at some certain distance of r. We know that if we go to the picture, we know that at r equal to r2, at this point, velocity vz is 0 because the wall is stationary. On the other hand, at this point, where r equal to r1, Vz supposed to go with the same velocity as a y itself. So we have two boundaries. First boundary, at r equal to r2, outside velocity Vz is 0 because the wall is stagnant. So taking Vz to be 0, right hand side you get C1 over mu ln R2 plus C2. Another boundary at R equal to R1, Vz is capital V, or velocity of the wire. Replace to the first equation, you end up with this one. So we have equation 1 and equation 2, two variables C1 and C2. You can solve for these two equations, and at the end, if you take equation 2 subtracted by equation 1, C2 will be cancelled. Right hand side you get V equal to minus C1 over mu logarithm of R1 subtracted by logarithm of R2, which can be combined into logarithm of R1 over R2. So from here, I can get minus C1 over mu to be capital V over logarithm of the radius ratio. Please note that I use minus C1 over mu because here can be replaced here right away. I don't need to worry about the minus sign at all. Once you get minus C1 over mu, I can take minus C1 over mu here. So from equation 1, I can solve for C2. And C2 would basically minus V over logarithm of R1 over R2 times logarithm of R2. So knowing minus C1 over mu and C2, then I can replace into the original equation, this equation, to get velocity. So Vz supposed to be equal to minus C1 over mu, which is V over logarithm ratio R1 over R2 times logarithm of R minus C2 plus C2, and minus C2 is minus by itself, so minus V over logarithm ratio R1 over R2 times R2, ln of R2. The rest is basically cleaning up. We have common term over here and over here, so take it out. Then we have logarithm of R subtracted by logarithm of R2, which can be combined into logarithm of R over R2. So that should be our velocity profile. Alright, if you want to do this problem using equation of change, we can start by using equation of continuity. This is equation of continuity for cylindrical coordinate. And we can say that steady state, this term is 0, or your density does not change with respect to time. VR is 0, V zeta is 0. So here you can take rho out of the differentiation because density is constant. At the end, you end up with dvz by dz equal to 0, or vz is not function of z, as we already found out. Then we can have equation of motion. Under the assumption of constant density and constant viscosity of the liquid, we can change equation of motion to Navier-Stokes equation. This is Navier-Stokes equation for cylindrical coordinate, and this is R component, zeta component, and z component. Okay, so let's start with R component. Steady state assumption, we eliminate this term, and all terms associated with VR is 0. So VR is 0. V zeta is also 0, so we can neglect the whole left hand side of our component equation. For pressure, we can leave pressure at the moment and handle the rest of the term first. V r 0, 0 here, 0 there, and V zeta is 0. So now we have to look at the term. We have pressure and we have gravity. So if we take account of gravity, there will be pressure in our directions. But if we neglect gravity, the pressure will be 0. In other words, from our component, what you have would be dP by dr equal to 0, or pressure is not function of r. For zeta component, we eliminate all the V zeta here, here, here. On the right hand side, all of V zeta will be gone, and we are 0. Same thing applied if you consider gravity, which in this particular problem there will be gravity in zeta direction. Pressure should appear, or pressure should change with respect to zeta. But if you neglect effects of gravity, the zeta component should give you that pressure is no longer a function of zeta. Alright, for Z component, steady state term, Vr is 0, V zeta is 0, Vc is not function of Z, whole term here is 0 according to equation of continuity we found earlier. And for this particular problem, pressure inside the die and pressure at the outlet of the die are equal, so pressure is not function of Z. This term can be dropped. Next term, this term cannot be dropped because velocity Vz is a function of r. But Vz is not function of zeta. This term can be dropped. Vz is not function of z. So the second derivative is also 0. This term can be dropped. And we neglect the gravity. This term can be dropped. So from z component, what you have should be mu over r d by dr r dvc by dr equal to 0. Please note that I use total differentiation because vc is function of r only. So from this vc from z component, you can eliminate this term. The whole term here can be eliminated because the right hand side is 0. Then you can take integration to have r dvz by dr equal to integration constant c1, and move r to the right hand side to get c1 over r. And then you can integrate vz equal to c1 logarithm r plus c2. Again, two boundary conditions are required, and we know that at r equal to r2, vz is equal to 0. So 0 equal to c1 ln r2 plus c2. Another boundary condition at r equal to r1, vz equal to capital V. So capital V equal to c1 logarithm of r1 plus c2. This is first equation. This is second equation. Two equations with two unknown of c1 and c2. If you take equation 2, subtract by equation 1, c2 would cancel out, and you have v on the left hand side equal to c1 logarithm of r1 over r2. or C1 equal to V over logarithm of R ratio, similar to what we got earlier, except the sign are a little bit different. Then if you plug this C1 here, you can solve for C2. So C2 should be minus V over logarithm of R1 over R2 times logarithm of R2. That would be C2. Then we can take C1 and C2 here and there so that we can find velocity profile. So Vz would be capital V over logarithm R1 over R2 ln R subtracted by C2 then just clean it up, take the common term and combine logarithm R and logarithm R2 to get the same answer as what we did earlier. The next problem asking for volumetric flow rate of the polymer or of the liquid. So what we want to find next would be volumetric flow rate or Q. In this case, Q or volumetric flow rate is basically taking the linear velocity multiplied by the area perpendicular to it. Mathematically, it means you take Vz and integrate it twice across the area perpendicular to the direction of Vc. In the direction perpendicular to Vc, supposed to be direction of R, so you integrate with respect to dr and integrate with respect to theta. So the coordinate, the limit of integration should go from R1 to R2 and then from 0 to 2 pi. But of course, according to calculus, integration in cylindrical coordinate, you need to multiply R in here. That's a part of the surface integration in cylindrical coordinate. Now, outside integration of d theta, you can get 2 pi right away because whatever inside has nothing to do with theta. The rest should be integral of R1 to R2 of velocity. Now we can take our velocity from above here. All right. Now this part, this is constant. So if I take it out of the integration, you get 2 pi v over ln R1 over R2. That would be our constant. And inside you have integration. Now we have this term, R, if I take R here, together with that R, you end up with integral R ln R dr. And then this term can be going up and get negative of integral of R1, R2, R ln R2. dr. And the integral requires some advanced calculus, but if you turn on the handbook, you see that from the handbook, integral of x ln x dx is equal to x squared over 2 of ln x minus half. So this is exactly the same as the red term. So I'm going to get q equal to 2 pi v over log r1 over r2 of inside integral of the red term. I should get r squared over 2 ln r minus half integral from r1 to r2. And then for the pink term, this is constant, so I can take it out, leaving r here by itself. Integral of r, you get r squared over 2 integral from r1 to r2. The rest is basically simple algebra. So I'm going to take the limit, upper limit, replace in everything inside. You get r2 squared over 2 logarithm of r2 subtracted by half minus lower limit of integration, which is r1. Minus half here. So that should be the first integral. The second one, basically you have minus ln of r2 over 2 and then r2 squared minus r1 squared. Alright. Then, if I take these two terms together, I get r2 squared over 2 ln r2 so this term is gone, appear over here. And then I have this term multiplied by this term to get r2 squared over 2 ln r2. That would be my pink term. And then this term and that term together get minus r1 squared over 2 ln r1 and this term multiplied by this term you get plus r1 squared over 2 ln r2. The rest should be this term and that term So I get minus R2 square over 4 plus R1 square over 4. So you see that this and that term cancel out. Eventually, I will get this nice and clean. R1 square minus R2 square over 4. I take these two terms together, subtracted by these two terms together, combined, you get R1 square over 2 logarithm of R1 over R2. So this should be your volumetric flow rate. Lastly, we can find force for Y pulling, or F in Z direction. Force can be calculated based on shear stress multiplied by the area. So we need to find shear stress first. If you go back to this part of the calculation, when we did the shear balance, you see that tau Rz, which is shear stress, is equal to C1 over R, and C1 was found already. If you search, you get C1 already over here. So if you take C1 and plug it back to this equation, you can get shear stress profile. So originally we have R tau Rz equal to C1, where minus C1 over mu equal to V over logarithm R1 over R2. This was obtained based on the boundary condition. So in this case, tau Rz should be C1 over R. Basically, it would be minus mu V over R ln R1 over R2. But the force that we are talking about here is supposed to be tau applied at the interface on the surface. So we need tau Rz at R equal to R1 on the surface of the solid wire. So if you take, or if you replace R here to be R1, you get tau on the surface. Then you plug into the force. So force itself is supposed to be tau Rz at R equal to R1, or shear stress at the surface, multiplied by the area, and the area is supposed to be the area that this shear stress apply upon. And the area, if you go back to the picture, the area here is supposed to be the surface area of the rod. And the surface area of the rod can be calculated based on the circumference of the rod or of the wire multiplied by the length. So the surface here supposed to be 2 pi r1 times L. Taking that back down here. So the area is 2 pi r1 times L. So taking this here and rearrange equation. You get the force to be minus 2 pi L mu V over ln R1 over R2, because this R1 and that R1 cancel out. So you have to keep in mind that this is the force that liquid acts on the solid. So if you want to calculate the force, the counter force the solid act on the liquid, that's supposed to be minus of this whole force. But the problems ask for the force that we, the human, has to act on a wire. So the force on the wire supposed to be equal to minus a force on the solid to the liquid. So eventually this should be your answer. If you checked 2 pi L mu are constant, V itself is going in plus Z direction. Alright, here underneath R1 is smaller than R2, so this is fraction, making logarithm of the fraction to be negative. We have negative over here and negative over there, making the force to be positive. That means the force that we need to pull the wire should go in the plus Z direction as expected.